Okay, so you knew it was coming eventually, that we'd have to bring all this together and do some word problems. I know that you guys have a special fondness for word problems, so I'm sure you really were looking forward to this, and you're really going to enjoy this. We'll try and get through this. It's a bit of a challenge. It takes a lot of thinking through, but again, once you have everything set up, most of the time, once you know what's being asked for and you get everything set up, it's just working through the algebra after that. So we'll try and see a bunch of different examples here and see different ways of setting up and going through them. So hopefully it's not too bad. So a couple things to remember here that functions, we look at equations, they do have a domain and range, but we've seen it before in some examples where there is a context to the problem that's going to give us additional restrictions beyond those that we see from the function. So for example, if you think about a parabola, normally the domain of any parabola is that x is an element of the real numbers. As any x value you can put in there, it will work. However, if you think about a situation where you have a parabola but the independent variable is time, well, most of the time we can't have a negative time, so that introduces a restriction there that the independent variable, the x or the t, whatever you're using, has to also be actually greater than or equal to 0. So little things like that can come into play, and we have to remember that when you get a final solution, you have to check to make sure whether or not it's acceptable given the fact that you have a real life situation. So we'll see some of that coming up, but just something to think of when you're getting a final answer with a word problem. So with word problems, I know that they can be a bit of a struggle, but some things that might help us out a bit is know what you're solving for. A lot of the time you'll see the word maximum or minimum, and then it should scream out to you that I'm looking for something to do with the vertex, but it won't necessarily be the optimal value. I mean, if it asks for the maximum or minimum, yes, it's the optimal value, but if it wants something like the length that it produces the maximum area, so you're looking for an independent variable that produces a maximum, that would be the axis symmetry. What price produces the greatest profit? Again, you're looking for a value that produces a maximum, that's an axis symmetry. It might be a problem where you're just solving it. It has nothing to do with the maximum or minimum. It might be a problem where you're looking for the initial value, which is the y-intercept. So it depends on the situation, but don't always assume you're looking for the optimal value. If ever you can, do draw a picture. When everything is drawn out, it can sort of make things fall into place a little bit easier. And you also want to make sure the equations that you generate actually make sense. These are going to be quadratic, so the equation that you generate should have degree 2. It can't be a line, right? Sometimes you need to create more than one equation to solve for. It might be a system of equations. And odds are, I'm not usually so mean that I'll give you a bunch of irrelevant information. So if there's something in the question that you haven't used yet, odds are you've made a mistake. So look for everything that's given you in the question is usually relevant to what's going on. So try and find a way to incorporate everything in. And just some things to watch out for here. If you're trying to determine a maximum, you see the word maximum in the equation, make sure that quadratic is actually going to be opening down when you come up with the equation. If you're looking for a minimum, make sure it's a quadratic that opens up. So things like that you can sort of do self-checks on yourself on the way to make sure that you're on the right track. Alright, enough of me talking. Let's take a look at an example. This is a typical type of setup that you might see where you're trying to do a fence, and we're trying to enclose a rectangular area with a certain amount of fencing, and we're going to try and usually try to maximize something. But in this situation, I want to try and find the domain and range of the area function. So what I'm going to do is I'm going to draw this out first, like I suggested. So we're told the farmer is going to use the river as one side of the enclosure. So I'm going to draw my river in here. And I'm building a rectangular area against that river. So let's say here I'm going to go 1, 2, 3 sides, and there's my rectangular enclosure. Now I know I have 340 meters of fencing in total, and I don't know anything about the dimensions here, so I'm just going to call them L and W. So if I want to find the area function, well, how do I find the area of a rectangle? Hopefully you remember from elementary or middle school geometry that the area is going to be equal to length times width. Okay, so that's a good start. The only problem is you'll see here that we actually have 3 variables. We have the area, but it depends on both the length and the width. So it's going to be hard for us to sort of create a relationship with what's going on with this many variables. So I mentioned on the previous slide that sometimes you have to create 2 equations, a system to try and solve. This will be one of those situations. We want to try to only have one variable over here so we can actually find the domain and range. So to do that, we got to find another relationship that exists between the length and the width. So what information have I not used yet in this problem? Well, it's this 340 meters of fencing. So that 340 meters of fencing takes up this entire perimeter right here. So 340 would be equal to a width plus a length plus a width, or equal to 2w plus L. Okay, so I can use that relationship here. This is my system, right? 340 is 2w plus L, and I have length times width over here. So what I'm actually going to do now is take this perimeter equation and isolate for one of the variables. Easiest variable to isolate for is going to be L, so this is going to give me L equals 340 minus 2w. Okay. And I can substitute that into my area function that I've just created. So area will be equal to, instead of L, it's going to be 340 minus 2w times w. Okay, so now again, the reason I did this is now there's only one variable on this side, in this case w, so my area depends on my width. Okay, so what I have here now is the equation of a quadratic, and it looks and is factored form. So again, if I'm trying to find the domain and range, what helps is to actually have a picture of what's going on here. So to have a picture, I need some key points off the graph. So from a factored form, the main things I can get are the zeros. So from here, I'm going to take a look at, okay, so if I want my zeros, I have two factors right here. So I get 1 when 340 minus 2w is equal to 0. So when I rearrange, solve for w, I get w equals 170. The other one I get over here is from when this factor was just w, where w equals 0. So there I have my two zeros. Okay, now that I have those zeros, that'll help me get a picture. Now remember, I'm trying to find the domain and range, so to get an idea of what's going on, let's just create a quick little graph here. Again, just a quick little sketch, not really to scale. So I'm going to have x-intercepts, or sorry, in this case w-intercepts, of 0 and 170. So if I create a sketch of what's going on, okay, the only thing I need to figure out now is, am I opening up or down? Well, again, remember, you can't always necessarily tell from factored form, but if you were to expand this out into standard form, I'd see up here that I'd have, just going to squeeze in here, I'd have negative 2w squared plus 340w. So looking at that a value in standard form, I can see right away I'm going to be opening down. So my graph's going to look something like this. Okay. Now you'll notice here that I'm not continuing the graph any further down here because my independent variable is width, my dependent variable is area, and I can't have a negative area. That doesn't make any sense. So there's my first sort of real life restriction here, is instead of a parabola just going to continue on forever downwards here, it's going to stop at 0 because I can't have a negative area. So that's going to be incorporated into our domain and range later. So right away now, looking at this equation, I can get my domain. I can see that my w is going to go no lower than 0 and go no higher than 170. So right away there, my domain is 0 is less than or equal to w, less than or equal to 170. Okay, so that part's done. Now for my range, I already talked about how the area can't be negative, so I know that the area has to be greater than or equal to 0. However, there's going to be a maximum area somewhere up here as well. I need to try and figure out what that is. So once I can figure out what this value is over here at the vertex, then I can put in my maximum value for the area and I'm actually finished the problem. Okay, so how am I going to find that maximum? Well, I have my zeros over here at 0 and 170. What can I find with that? Well, halfway in between I'm going to have the axis symmetry, and the axis symmetry is going to help me see where the maximum value is. So you can probably eyeball with the axis symmetry. It's halfway between 0 and 170. You may be able to see that as being 85. But we can always calculate it as well. So axis symmetry, so it won't be x, it'll be w. I'll just have 0 plus 170 over 2. That'll give me 85. So all that's left to do now is to find that maximum value, put into the equation for a. So a will be 340 minus 2 times 85. And then all times 85. So run those things through your calculator, see what you get. I get 170 times 85, which gives me a maximum value of 14,450. And that's going to be square meters. Okay, so putting that on the graph that we have here, my maximum value is now 14,450, and now I can finish my domain and range. So my range, my area have a maximum value of 14,450. And it's what seemed like a simple problem at first, find the domain and range, became very, very complicated very quickly. But again, just by setting up the equation and finding everything we know about it, we can create a sketch and use the real life restrictions we have that we can't have negative area or negative dimensions, and wind up with our domain and range. Okay, so now for B, it asks for which dimensions will maximize the area. Now, the good news about this, we've actually already kind of figured all this out with all the work we did find the domain and range. So we already know that the maximum area is going to occur when W is equal to 85. Okay, so right from up here, we know the width is going to be 85 meters. And now we just need to find out the length. So probably the best way to find out the length is to look back all the way up here, back where we started, and remember that we only had 340 meters of fencing. So 340 is going to be equal to 2 widths plus a length. And we actually came up with an equation later because we were isolating for L. So L is going to be 340 minus twice the width. So we know that's true. Let's find the length. So we got 340 minus twice the width. We throw in the 85 there for W, and that's going to give us 170. Okay, so dimensions of 170 and 85 will maximize the area. Okay, so let's move on and try another one. So we've got two numbers that have a difference of 19. I try and figure out these numbers. We have another restriction on there that the sum of 17 less than 3 times the larger and the square of the smaller is a minimum. That's a very, very sort of long, complicated statement here. We're going to try and translate that into a math equation. I'm going to let you try and think through that on your own, try and create the equations. We're also, the two numbers have a difference of 19. So just to at least start this up for you guys, we have to define our variables. So I'm going to let, let's just let A be the larger number. And they have a difference of 19, and we're going to then let B be the smaller number. Okay, and what we know is that two numbers have a difference of 19, so I'll start you guys off here and say the larger number minus a smaller number, so A minus B, is going to be equal to 19. Okay, that doesn't help us create a quadratic equation to solve, because we're trying to minimize something. So we're trying to minimize the sum of 17 less than 3 times the larger and the square of the smaller. That's the whole thing we're trying to minimize. So try and create an equation for the sum of 17 less than 3 times the larger and the square of the smaller. It's trying to translate those words into a math equation can be kind of tricky. So give it a try first, and then we'll see what you get. Okay, so again, this is going to be a very complicated equation to try and set up, because this is what we're actually trying to minimize here. This is the big one that's important here, the second equation here. So it's the sum of, so we're going to be adding two things together, 17 less than 3 times the larger. So if we take 3 times the larger, which is 3a, we want 17 less than that, so it gives us 3a minus 17. Now, I'm adding that because it's the sum of the square of the smaller. My smaller number was b, so I'm adding b squared. So I end up with 3a minus 17 plus b squared. And I don't know what to call it, I just called it n. It's to be equal to that whole expression there. And this is what I'm trying to minimize. Now, when you see the word minimum, you're thinking something to do with the vertex. Okay, so either the axis symmetry or the optimal value. But again here, before we even think about that, we've got two variables here. We've got a and we've got b. That's not going to work for us. We have to find some way of eliminating one of these variables. So what I'm going to do here, I'm going to look at this other equation here where the two numbers have a difference of 19, a minus b equals 19, isolate for a variable, and sub it into the equation. Now, they both look pretty easy to isolate for. I would choose to isolate for a because substituting something in for a into this guy right here is a lot easier than substituting something in for b over here where you then have to square it, and then have to FOIL it out or multiply it out using an array. So I would isolate for a in here and sub it into this equation. I'll let you try that, and we're going to continue this in part 2.